Today's lesson, aldehyde ketone versus carboxylic acid. First of all, let us clarify the lesson. Aldehyde. Suppose this one. This is a kind of aldehyde. Its name is acetaldehyde or ethanol. Again, ketone. For example, this one. This is a kind of ketone. Its name is dimethyl ketone. This is also known as propanone. Aldehyde that contains carbonyl group. Similarly, ketone that contains carbonyl group. Aldehyde and ketone undergo nucleophilic addition reaction to the carbonyl carbon. Similarly, nucleophile combines with carbonyl carbon of the ketone. That is, simply aldehyde and ketone undergo nucleophilic addition reactions. Aldehyde and ketone that contain carbonyl group, CO group, undergo nucleophilic addition reactions. Nucleophile combines with carbonyl carbon of aldehyde and nucleophile combines with carbonyl carbon of ketone. That is, simply aldehyde and ketone undergo nucleophilic addition reaction. But carboxylic acid, for example, this one. This is carboxylic acid, which is acetic acid. This is also known as ethanoic acid. Ethanoic acid that contains CO group, carbonyl group, but when this is treated with a nucleophile, then nucleophile cannot form bond to the carbonyl carbon. That is, no nucleophilic addition reactions by carboxylic acid. Similarly, like carboxylic acid, this compound, this is acetamide. This is also known as ethanamide. Though it contains carbonyl group, it doesn't undergo nucleophilic addition reactions. Again, another compound. This is a kind of ester. Its name is methylethanoate. Though it contains carbonyl group, nevertheless, this doesn't undergo nucleophilic addition reactions. These are derivatives of carboxylic acid. That is, carboxylic acid and its some derivatives do not undergo nucleophilic addition reactions, but aldehyde and ketone undergo nucleophilic addition reactions, though both the compounds contain carbonyl group. What is the reason behind this? This is today's lesson. So let's begin. Aldehyde ketone versus carboxylic acid. First of all, let us see nucleophilic addition reactions of aldehyde and ketone. Aldehyde, suppose this one, acetaldehyde or ethanol. When This ethanol is treated with nucleophile. It's a kind of nucleophile, neutral nucleophile. This nucleophile combines with carbonyl carbon because carbonyl carbon becomes positive in charge, delta positive in charge, oxygen becomes delta negative in charge because oxygen's electronegativity is higher than carbon's electronegativity. That is why nucleophile can attack this carbonyl carbon. As a result, this compound is formed. This is final product. Its name is 1,2,1-amino ethanol 2. 1-amino ethanol 2 is formed when aldehyde is treated with nucleophile. That is, simply we can say that aldehyde undergoes nucleophilic addition reaction. Again, ketone. When ketone is treated with nucleophile, neutral nucleophile ammonia, this ammonia attacks the carbonyl carbon because of its positive charge. As a result, this is formed. This is final product. Its name is 1,2,3,2-amino propanol 2. Two-amino propanol 2 is formed when ketone is treated with nucleophile. That is, simply nucleophile as well undergoes nucleophilic addition reaction. Now let us see mechanism of the reaction. Nucleophilic addition reactions of aldehyde and ketone. Mechanism is like this. Step 1, aldehyde, ethanol. First step, ethanol undergoes polarization. As a result, this entity is formed. Here hydrogen, carbon becomes positive in charge. This is step number 1. Step 2, nucleophile ammonia. This nucleophile forms chemical bond to the carbonyl carbon, positively charged carbon. As a result, this is obtained oxygen negative charge, here hydrogen with carbon, ammonia, as nitrogen. Nitrogen of ammonia forms coordinate covalent bond, giving its lone pair of electrons to the carbon, positively charged carbon. That is why over nitrogen positive charge develops. Because of this positive charge, these nitrogen hydrogen bonding electrons move towards nitrogen to vanish this positive charge, and this hydrogen gets freed as proton. This proton combines with this negatively charged oxygen. As a result, this is obtained CH3, carbon, oxygen. With this oxygen, this hydrogen, with this carbon, hydrogen, and with this carbon, NH2 amino group. That is one amino ethanol 1. One amino ethanol 1 is formed when aldehyde is treated with nucleophile. That is, aldehyde undergoes nucleophilic addition reaction. Now let us see reaction mechanism of nucleophilic addition reaction of ketone. Reaction mechanism of nucleophilic addition reaction of ketone. Ketone, for example, this compound, dimethyl ketone or propanone. In the first step, propanone, that is carbonyl group of propanone, undergoes polarization to form this entity. Oxygen becomes negative in charge, carbon becomes positive in charge. When this is treated with ammonia, neutral nucleophile, then this nitrogen forms chemical bond to the positively charged carbon to form this entity. Oxygen is negative in charge, methyl group, here NH3. Nitrogen forms bond to carbon, positively charged carbon. That is why this positive charge shifts to the nitrogen. Now, because of this positive charge, these nitrogen-hydrogen covalently bonded electrons move towards nitrogen to vanish this positive charge. As a result, this hydrogen gets freed as proton. This proton combines with this oxygen, negatively charged oxygen. As a result, this is found carbon, oxygen, hydrogen. Here CH3, here NH2. That is 2-amino propanol 2. 2-amino propanol 2, which is formed through addition of nucleophile to the ketone, that is propanone. That means ketone as well undergoes nucleophilic addition reaction. That is to say, aldehyde and ketone undergo nucleophilic addition reactions. Now let us see what about carboxylic acid. Now, carboxylic acid. Let us see one example of carboxylic acid. This is a kind of carboxylic acid. Its name is ethanoic acid or acetic acid. When ethanoic acid is treated with nucleophile, same nucleophile, ammonia, ethanoic acid, that is carboxylic acid, contains carbonyl group. Nevertheless, like aldehyde and ketone, carboxylic acid that contains carbonyl group doesn't undergo nucleophilic addition reactions. Now let us see the reason behind this. Carboxylic acid. Here, like aldehyde and ketone, carbonyl group of carboxylic acid gets polarized. As a result, this is formed. Oxygen becomes negative in charge, carbon becomes positive in charge. We know that oxygen contains two pairs of electrons. Oxygen carries two pairs of electrons, and the carbon which is nearer to oxygen is positive in charge. Now there is a chance of nucleophile ammonia to attack this positively charged carbon of carboxylic acid. But before the attack of the nucleophile to positively charged carbon, this lone pair of electrons turn into bond pair to vanish this positive charge. At the time, this positive charge shifts to the oxygen to form this entity CH3, carbon, oxygen negative charge, here double bond, then hydrogen. Positive charge of carbonyl carbon shifted to the oxygen. That is why nucleophile ammonia cannot attack this carbonyl carbon. Because of the presence of lone pair of electrons over oxygen, nucleophile cannot attack this carbonyl carbon because positive charge of carbonyl carbon is vanished by lone pair of electrons of oxygen. That is why we can say that carboxylic acid doesn't undergo nucleophilic addition reaction because of the presence of oxygen, because of the presence of lone pair of electrons over oxygen, because these lone pair of electrons take part in resonance. Through resonance, positive charge over carbon is vanished, is shifted to oxygen. That is why ammonia cannot attack the positively charged carbonyl carbon. So carboxylic acid doesn't undergo nucleophilic addition reactions, though it contains carbonyl group. Now, derivative of carboxylic acid. This is ethanamide or acetamide. When this is treated with nucleophile ammonia, in this case ammonia is supposed to attack this carbonyl carbon because this carbon becomes positive in charge because of the higher electronegative element oxygen. But after getting polarization, lone pair of electrons of nitrogen turns into bond pair. At the time, positive charge of carbon shifts to the nitrogen to form this entity. Carbon nitrogen single bond turns into carbon nitrogen double bond. Positive charge shifted to nitrogen. Then nucleophile cannot attack this carbonyl carbon because its positive charge is already vanished by lone pair electrons of nitrogen. Like carboxylic acid derivative, that is ethanamide or acetamide, doesn't undergo nucleophilic addition reaction. Now let us see another carboxylic acid derivative. Another carboxylic acid derivative, that is ester. This is a kind of ester. Its name is methylethanoate. Methylethanoate that contains carbonyl group, CO group, in which polarization occurs. As a result, this is formed. Carbon becomes positive in charge. Now, there is a chance of nucleophile to attack this carbonyl carbon. But before the attack of nucleophile to the carbonyl carbon, these lone pair of electrons turn into bond pair to vanish this positive charge, to form this entity, negative in charge, carbon oxygen double bond, here methyl group, positive charge shifted to oxygen. In this case, no way to attack of nucleophile to the carbonyl carbon because its positive charge is already disappeared. So we can say that aldehydes and ketones undergo nucleophilic addition reactions, but carboxylic acid and some derivatives of carboxylic acids do not undergo nucleophilic addition reactions because of the presence of lone pair electrons nearer to the element of carbonyl carbon. Now let us see resonance structures of carboxylic acid and resonance structures of derivatives of carboxylic acid. Carboxylic acid, for example, this one, acetic acid or ethanoic acid. Resonance structures are like this. Pi bonded electrons move towards oxygen because oxygen's electronegativity is higher than carbon. As a result, this structure is obtained. Oxygen becomes negative in charge, carbon becomes positive in charge. Here, oxygen carries two pairs of electrons, two lone pairs of electrons. Then these lone pair of electrons turn into bond pair and positive charge shifts to the oxygen to form this structure CH3. Here oxygen, negative charge, double bond, oxygen, positive charge. Here hydrogen. Again, these lone pair of electrons turn into bond pair. This bond pair of electrons turn into lone pair. That is, this structure is obtained. These are the resonance structures of carboxylic acid. As a result, positive charge over carbon is disappeared. Due to this, nucleophile cannot attack this carbonyl carbon. Resonance structure of carboxylic acid derivative. Ethanamide. Here, carbonyl group polarized to form this entity. Oxygen becomes negative in charge, carbon becomes positive in charge. Nitrogen contains one pair of electrons, lone pair of electrons. These lone pair of electrons turn into bond pair and positive charge shifts over nitrogen to form this structure. Oxygen with negative charge, carbon nitrogen double bond, nitrogen with positive charge. Again, these lone pair of electrons turn into bond pair. This bond pair of electrons turn into lone pair. That is, this structure is obtained. These are the resonance structures of ethanamide. Because of these resonance structures, carbon atom of carbonyl group cannot be positive in charge. That is why nucleophile cannot attack the carbonyl carbon of carboxylic acid derivative acetamide. Resonance structures of carboxylic acid derivative. It's a kind of ester. Carbonyl group of carboxylic acid derivative gets polarized. Oxygen becomes negative in charge, carbon becomes positive in charge. Oxygen carries two lone pairs of electrons. Here, these lone pair of electrons turn into bond pair. Positive charge shifted to oxygen to form this resonance structure. Oxygen becomes negative in charge. Carbon oxygen double bond is formed. Here CH3 over oxygen positive charge. Now these lone pair of electrons turn into bond pair. These bond pair of electrons turn into lone pair. That is, previous structure is obtained. Through these resonance structures, carbonyl carbon loses its positive charge. That is why nucleophile cannot attack this carbonyl carbon of carboxylic acid derivative. This is the reason of not undergoing nucleophilic addition reaction by carboxylic acid and carboxylic acid derivative. This is all about aldehyde ketone versus carboxylic acid. No more today. Thank you very much.